Hi everyone, my name is Amelia and I will be teaching this pre-recorded Teaching English in Poland virtual class, and it's called What is Engineering? So let's go ahead and get started. First things first, a little about myself. So my name is Amelia and I was born in Vancouver, Canada. I grew up in the United States, both in California but mostly in North Carolina, and both my parents are from Poland, so we spoke Polish at home growing up. And so I went to college in North Carolina and I studied mechanical engineering, and I just graduated last year in 2019, and then I moved to Europe where I am now doing a 2-year master's in electrical energy engineering. So my first year was in Sweden, and I'm about to move to Belgium for my second year. And so last year I participated in the Olsztynek Teaching English in Poland camp, and it was an amazing, amazing experience. I was a teacher assistant and I helped to organize afternoon activities for all the campers and students there. And then I was planning to go back this summer to teach a STEM course. So for those of you who do not know, STEM is an acronym which stands for science, technology, engineering, and mathematics. So I remember when I was in high school and I was thinking about college and what I should study in college, I had no idea what engineering was. And I liked math and I liked science, but I still didn't know I would end up studying STEM or engineering specifically. And so I hope this session today will teach you more about what engineering is. And even if you think you don't like math or science, that you walk away from the session and you learn something new. So that's my goal for today. What we're going to do is first start off with some background, just good information to know about engineering and different careers and paths that you can take. I'm going to do a little demonstration with my Arduino, and if you have no idea what an Arduino is, don't worry, we'll talk about it. It's just basically some fun electrical engineering, and then I'll also share with you a few resources. So if you like what we did today and want to learn more on your own time, you will be able to. So let's jump in. What is engineering? Take 10 seconds and think about what is the first thing that comes to your mind when someone says engineering? Just think about it. All right, so hopefully you've thought about what is engineering. And so now I'll give you a definition. Engineering is the application of science and math to solve real-world problems. Yeah, it's not super technical. It doesn't have to be building something. It doesn't have to be creating something. It's basically just problem solving. And so it's really a way of thinking, a mindset, and that's really what I kind of want everyone to grasp from the session, that it doesn't have to be very technical. It just has to be, you have a problem and you have to find a way to solve it. So what are some examples of common engineering fields? Maybe when you were thinking about what is engineering, you thought about some of these. For example, mechanical engineering, what I studied for my bachelor's. When someone thinks mechanical engineering, a lot of times they told me, oh, Amelia, you want to build cars, right? Well, building cars is, yes, a car is a mechanical system, for sure. And mechanical engineers do design cars, but it's really any sort of mechanical system. So not only cars, but turbines and engines, machinery, tools. A really big field right now is robots and automation and these kinds of processes that, humans are turning over to machines and having robots do things for them. And that's all in mechanical engineering. Another common field is civil engineering. So if we think back to, for example, the ancient Roman Empire, they were kind of the first engineers, really. They built really amazing structures, bridges, aqueducts to bring water, roads that still last and are found nowadays 2,000 years later. But the modern field of civil engineering is designing and building public works, such as bridges, roads, houses, structure, buildings, tunnels, and more. civil engineering can also encompass architecture, for example, and design. So it's a more creative field, not as technical as, for example, civil engineering would be. Another big field is chemical engineering. So chemical engineers transform raw materials and elements into useful products that then humans can use for anything. So, for example, plastics, paper, dyes, energy, fertilizers, pharmaceuticals. Really big one is pharmaceuticals and medicines, actually. So engineering the different chemical combinations and components to make a cure for a disease. That's a really, really big one. As well as aerospace engineering. So mechanical engineering was with cars. So now we have aerospace, the design, testing, and manufacturing of aircraft, spacecraft, satellites, and missiles. So, for example, NASA has a lot of aerospace engineers. Boeing, Airbus, these are big, big companies that deal with aviation and aerospace. But there are also engineering fields that you might not have actually thought of when you were brainstorming. So, for example, biomedical engineering. It kind of integrates a lot of different engineering fields, such as mechanical and chemical, to design solutions specifically for biology and medicine to improve human health. So, actually, a lot of my friends studied biomedical engineering, and they had a variety of interests in this field, such as building good equipment for diagnosing diseases, also for treating diseases, for prosthetics, artificial limbs, artificial bones, implants into the human body, as well as more chemical-based medicines. And it's a really, really big and exciting field right now, I would say. There's also environmental engineers. So these people develop solutions for environmental problems. So that includes recycling, waste disposal, public health systems, sanitation, water, sewage sanitation systems, as well as solutions for water and air pollution. So, for example, if there is an oil spill, environmental engineers would assess the damage and what needs to be done to clean it up. For example, they're working on cool algae that would eat the oil, so to prevent the spill from spreading. It's some also really, really cool stuff, and a field that is actually really growing as well over the past few years. We also have computer engineers. So these people design and develop the software and the hardware for any sorts of computers. So the computers like your laptops and personal computers you might be thinking of, as well as phones and wireless communication networks and more. And it's very closely related to electrical engineering, which designs and develops technology for electricity, power transmission, magnetism, signals, telecommunication. Electrical engineering has been a field that's really developed over the last few decades. And actually it's the field that I am studying for my master's program right now, specifically energy and the energy grid that basically connects all of us really and makes sure you have power in your home. So that's the project that we're actually going to be working on, is an electrical engineering project. And specifically energy engineering, which is kind of like a subset of electrical engineering. They work with designing and developing smart and sustainable energy systems, so different types of renewable energy. So here we have, for example, wind turbines, solar panels, biofuels. Not pictured is, for example, hydropower, taking water, harnessing energy from water, rivers, streams, as well as tides in the ocean. But it's a really, really exciting field, and especially as the EU and the US are setting goals to move away from fossil fuels, such as carbon, coal, natural gas. As we move away from those and transition into more sustainable energy sources that are renewable, that don't expire, like the energy from the sun that's converted by solar panels into electricity, the energy from the wind that is converted into electricity, using biofuels, for example, sunflower, corn is another big one that we can then transform into biofuel and power our cars instead of using gasoline. which can lead to a lot of issues with smog and air pollution. I know that is a big problem in Poland, especially in the south. So this is a really exciting field because I think there's a lot of potential to be done and that needs to be done into the future over the next few years. So now that we've talked a little bit about all of the different types of engineering, I want to demonstrate just one tiny example of electrical engineering with a Arduino demonstration. So what is an Arduino? An Arduino is this. So basically it's a little circuit board with a lot of fancy components. But basically what it does is that with this wire, it plugs into my laptop and it allows me to write some code and control essentially what happens on the circuit board. So it's very easy to use. It's very modular because I can do anything I want with it. I can create all sorts of different projects. And these are becoming more and more popular for educational purposes in colleges and universities because they're not expensive at all and they're very easy to carry around and do different projects with. So let's jump into some terminology before we jump into the demonstration. First thing is voltage. So voltage is the difference in charge between 2 points. So you might be thinking, what is charge? Well, charge is basically how much electrical force something has, and it can be positive or negative. So let's take, for example, a battery. We have all seen batteries, right? It's just something that stores energy in the form of chemicals because there are basically some specific chemicals in here that store energy. However, the battery has the positive end and the negative end, and that means that there is a voltage drop or a voltage difference between these two ends because there is positive charge here and negative charge here. The next word is current. So current is the rate at which charge is flowing. So for example, just like this, the battery can't do much, right? Because it's not connected to anything. These ends of the battery, these silver ends, they're called terminals. And these terminals, well, they're not connected to anything because they're just connected to the air right now. However, take, for example, what if I were to connect the ends of the battery with a wire? This is just like a paper clip that I took apart. Well, first of all, if I were to do this, it can get very hot because I would create a circuit. Basically, I would close the loop and connect the two terminals of the battery, and that would mean electricity would be flowing from this positive end through the wire and into the negative end. So it would be like a loop with electricity flowing, and that means this wire would get hot. So I don't recommend doing this, but just to illustrate the concept, we have the voltage drop in the battery. We connect the wire, and this means that a current will be created in the wire, and the current will run from the positive through the wire and into the negative. And our last word is resistance. So resistance is a material's tendency to resist the flow of charge. So when I have this set up, this material of the wire, there is some sort of inside resistance in this material. It's not perfect, and it's not like the charge that's coming out of the positive end will immediately go to the negative end. No, it has to travel all the way through the wire. And the resistance, the material's resistance of the wire can change the speed at which the charge flows. So we can change the current if we have the constant voltage. Actually, on the battery, you can see that the battery has a 1.5 voltage rating. So that means all AAA, because this is, yes, 3A batteries have a rating of 1.5 volts. So how are voltage, current, resistance related? Well, voltage V is equal to the product of the current I times the resistance R. So that means in a battery, which is already 1.5 volts, we can either change the current to the resistance, but it has to equal 1.5 volts. So we can change out this wire. Maybe we can get a copper wire, a better wire that can conduct faster because it has less resistance. That means the current will increase. Or we can get a worser wire with more resistance, and that will mean that the current will decrease. We can also make an analogy kind of to mechanical systems. So if you're still kind of confused about all this electricity, voltage stuff, how were things traveling like inside a battery? Yeah, I didn't really understand it at first either, so it took me a while. But what helped was this analogy. If you think about voltage as being the pressure in a tank of water, so here we have in this water tank a lot of water. And there's only this little pipe at the bottom. So the water flowing through the pipe represents the current, the electrical current. And this pipe has a very small diameter. It's a very small pipe. And so it restricts the flow of water just like a resistor restricts the flow of current in a circuit. So if we had more water in this tank, we would have more voltage because there would be more pressure pushing down through this pipe. If we had less water, there would be less voltage because we'd have less pressure. And of course, if we had more water, the current would also be higher because we'd get more pressure pushing through the same pipe. If we wanted to change the resistance of the circuit, like we were talking about switching out different wires, that would be like switching out different pipes. So having a bigger pipe versus a smaller pipe. So hopefully that makes a little bit more sense now. So now we can jump into building our Arduino demonstration. So here, we'll lower the camera so you can see. We have the Arduino and we have our breadboard. The breadboard is basically a board where we can build our circuit, and it allows us to connect all the wires and the components together. And so what we need to do is hook it up to the Arduino, and then I'll explain to you the code that you see on the left side of the screen, and then we can, well, go ahead and get started. So this demonstration is called traffic light. You can see I have a red, yellow, and green light. And I have 3 corresponding wires, the green, yellow, and red wires that are currently not connected to anything, but I have to hook them up to our Arduino microprocessor. So I'm going to put the green wire in slot number 8, basically to connect like the input and the output. So you remember I said that the Arduino microprocessor was connected to my computer with this laptop. So my computer is going to send the signals from the code through this cable and into the breadboard to basically control the switching of the lights. So you can see in the code here that green is 8, yellow is 9, and red is 10, and that just refers to the terminals on the Arduino. All right, we also need to connect our power to power the breadboard. So red is our power, and I'm going to connect it to 5 volts, and black is our ground, which basically just acts as a reference point for our circuit. Everything else on the breadboard I have already connected. So I'm just going to explain it really fast. Basically, these are LEDs, which are light emitting diodes, which are basically small lights that we will use for this demonstration. These 3 elements are the resistors. So they are lined up before the LED just to prevent the LED from heating up. If there is too much current going into an LED, it can burn out and basically kill off the LED, burn it out. So we would have to replace it and use another one. And you can see here from the Arduino, we have the red, yellow, green input wires coming in. these are all connected in the same row on the breadboard as the resistor. And then after the resistor, it connects to the LED. And they're all connected. So after the current passes through the LEDs, it goes into ground. So that neutral, kind of like off point. And that ground and the power as well, it's all connected again back to the breadboard because it's going to use the energy coming in from the cable from the laptop. Awesome. So looking at this code on the left here, these are just defining the import terminals so that my code will know where to send the signals to based on whether it's the red, yellow, or green LED we're talking about. So a few quick comments about the Arduino code before we go ahead and run the circuit. Arduino code is written in C++, and C++ is a coding language that is written in English. So, I mean, you can see when you look at this code, we have words like setup, void, loop, delay, digital write. These are all English words, right? So a lot of coding languages, C++, Java, they're all based in English. So actually learning English, you're already learning a lot of coding languages too, which is really cool. The thing is, it also makes it easier to program. And so I already explained the first few lines, the int red, yellow, green, just basically associates those input terminals on the Arduino microprocessor 8, 9, and 10 with the different color of the LED lights. The next few codes also just make some more setup that the 3 LEDs are output. So it's going to be the laptop is sending the code, is sending an output signal to the LED lights to control them. And then one thing to know also about code, Arduino code, is that it runs in a loop. So it basically runs to no end because there isn't a natural end in the software. I have to remove the cable to actually make it end. All right, so I won't go through the code yet because I want to run the circuit and then look at it first, and then we'll talk about it. So here it is, and I am plugging it in. Here we go, yellow, red, and yellow, green. All right, so let's take a look at the code. It starts off with green off, yellow on for 1 second. So it's about to loop again, so let's watch out for the start. Yes, yellow on for a second, red on for a second, both green. So that's what is programmed right now, right? We yellow on for 1 second, we turn off yellow, then red on for 1 second, then both red and yellow on, and then we turn on green. So we can play around with this code a little bit. Of course, if we wanted to change the duration, we would change the delay time. So again, 1000 milliseconds, 1 second. We can bump it down, bump it down, or ramp it up. We can also change the colors that are changing, which is easy because we had previously referred to green 8, yellow 9, red 10. We can refer to the terminals just by the names of the color. So green, yellow, easy. And we can also change out the LEDs and the resistors as well. Remember, we put in these resistors at the beginning so to prevent the LEDs from burning out. But what we actually could do is to put resistors with a higher rating, so with more resistance. And if you remember back to the equation V equals IR, if we increase resistance with the same voltage, the current will go down. And so with less current to the LEDs would become less bright. So that's just one example, or actually several examples of changes that we can make. The cool thing is this is a very, very simple Arduino demonstration, and there's a lot of different projects that you can do that different people have done. They put them all online, and you can basically read about how to do them. A lot of Arduinos also can be adapted to include like motors, different sensors. So there are a lot of really cool projects out there that have utilized these, um, especially for just like little tricks and hacks around the house, um, which is really cool. So let's do a little recap based on what we learned about the basics of electric circuits earlier as it applies to the Arduino. So you'll remember that electric circuits are ruled by the equation V voltage equals I current times resistance R. And you'll remember that I plugged in the red wire to power. It was 5 volts from the Arduino going into our breadboard. And then that's voltage. And then there's current flowing through the breadboard, through the resistors, and then through the LEDs, depending on which LED we were turning on at that time. And that was governed also by the microprocessor of the Arduino, because it was sending signals from my computer code to say which LED we wanted to turn on or have off at that time. Remember also that if we were to change out the resistor with more resistance, based on the equation, we'd have less current and the LED would then be shining a weaker light. Similarly, with the battery, again, don't do this because it can get very hot, but if we were to close the circuit, then there would be a current flowing from the positive terminal of the battery through the wire, all the way through the wire to the negative end. And this would be a closed loop. But the battery is a little bit less voltage because it was 1.5 volts. This was at 5 volts. So just to keep in mind. But this is really just fundamental electronic circuits governed by this equation. If you like this and you choose to study electrical engineering, then this is the basic. This is the 1 + 1 = 2 of electrical engineering. What I'm going to do is to share with you all some resources that I use myself and I think are very helpful if you enjoyed today's session and are interested in learning more. So tryengineering.org is great for you to explore different engineering careers, meet real-life engineers, and hear what they're working on a daily basis, because I think you'll find that a lot of the engineering fields overlap with each other, and just because you studied one thing doesn't mean you'll work with another thing. The great thing about engineers is that they are versatile and adaptable and flexible and can problem solve anything, really. MIT OpenCourseWare has really great courses and teaching materials that are all available online for free to check out as well. And then YouTube, good old YouTube, has great videos about coding and home projects. The great thing about coding is that anywhere anyone is in the world, if you have a laptop, you can learn how to code. With YouTube videos about, for example, Java. For Java, you don't need to have any sort of additional program. You can code right on your laptop or your computer. So it's one of the first and easiest programming languages to learn. That being said, it's also quite hard, but it's also quite easy to get going. And lastly, Engineer Girl has really great resources for women in STEM. I remember really, for me, when I was in a class with me and all guys, it was very intimidating. But I've been very fortunate to be surrounded by a great network of women in STEM, and I only hope to expand it, and hopefully all of you who were with me today took out a few good lessons from this session. So I want to say thank you, and if you have any questions, any comments, any ideas, and you want to know more, please don't hesitate to reach out. I love talking with you, and I'd love to be a resource if you need anything ever. So you can email me at my email address. It's listed there on the screen. And thank you. I hope I hear from you.